This would be the Catagen Tech Talk. So Dr. Andrew Woods and Dr. Kurtis Irwin from Catagen would be sharing with us their presentation on testing and after-treatment systems to meet emissions legislation. So I'll turn it over to Catagen.
Thank you very much, Madhu.
Okay, so good afternoon, everyone. Thank you for the introductions from Dr. Andrew Woods and from the Ghana team. Today, I'll go through some slides detailing who Catagen are, a bit of detail on our recirculating reactor and how we have world-leading catalyst testing facilities and capabilities. Just a little bit more of a background around me. From Andrew was saying, so I'd done 6 weeks placement in India, where we worked with the Indian Railway Institute of Mechanical and Electrical Engineers. And it was quite exciting to be there and really to experience the Indian culture. And that was an exchange program, so we were able to then have some of the Indian students return to Belfast and Queen's University. And really, I hope to be able to continue developing the relationships with the Indian culture and back here in Belfast. So first of all, who are Catagen? We are an after-treatment testing and emissions specialist company. We help OEMs, fuels and additives and lubricant companies from around the world meet their development requirements. And we use our unique recirculating reactor to replicate a range of engine out conditions across multiple applications. And the processes in place allow us to deliver accurate and reproducible outcomes for catalyst aging, performance measurements, and after-treatment system poisoning. So briefly, we mentioned earlier, Catagen's main purpose is to clean and decarbonize the air. And we're able to do this by offsetting any CO2 that would be used in engines by applying our recirculating technology, which uses up to 98% less CO2 when compared directly to an engine. To date, we have displaced over 1,100 tons of CO2 from January 2017. And as we have said, we have some of the world leading experts in catalysis and after-treatment systems with over 70 years of combined experience in the industry. We have 5 PhDs specifically in catalyst aging, catalyst performance, catalyst modeling and simulation, and we also have a current ongoing PhD into catalyst characterization. So we're currently offering and applying our services across a number of different industry segments, aiding in development and homologation of these after-treatment systems around the globe. We are working with over 20 of these leading OEMs across multiple industry segments, and our technologies and methodologies have been certified globally through the Vehicle Certification Agency in the UK and SIAT in Europe. And we've also supported OEMs with type approval for the US with the Environmental Protection Agency and CARB, the California Air Resource Board. And so why do Catagen have such great working relationships with these leading OEMs? Not only offer the world-leading services and data quality, but are also able to reduce costs and have significant CO2 savings. So why must we test after-treatment systems? It's important to understand why we need to age and understand the performance of after-treatment systems. And there is a concern throughout surrounding emissions and air quality, particularly within the automotive industry, where the transport sector is found to be responsible for approximately 15% of the emissions. For this reason, exhaust emissions legislations are becoming more and more stringent, causing an increased pressure on the effectiveness and efficiency of after-treatment systems, forcing a reduction of 83% of harmful tailpipe emissions from first legislations. The increased durability and OBD2 requirements will require more accurately tested after-treatment systems to allow for the most optimized powertrain systems. So I want to move on now to give a little bit more detail about the Catagen patented recirculating reactor. So at an early stage, as Andrew mentioned earlier, we understood that there was something missing when it comes to testing and understanding full-scale after-treatment systems. It is understood that testing in laboratory on cores and small scales, while it may be accurate and repeatable, it was not representative. And while engine testing is representative, it is not always as accurate or repeatable from time to time to be to help us fully understand catalyst development. So the Omega Reactor was developed to allow for high accuracy, high repeatability on full-scale aftertreatment systems that are representative of on-road aging and characterization. So here we can see a schematic of the Catagen Omega Reactor. Aging is performed on full-scale exhaust systems, and we're able to fit any size of aftertreatment with the modular design. The Omega Reactor is capable of controlling inlet temperatures up to 1000 degrees Celsius, flow rates up to 80 grams per second and greater depending on the application, and a gaseous composition mix of any composition depending on requirements. A common example for simple engine out conditions of air, carbon monoxide, hydrocarbons, and nitrogen oxides. So I'm going to now take a look at a specific example of an industry challenge that Catagen and their partner KTM have been able to overcome. The OBD2 threshold limit is very difficult to achieve due to the ever-improving engine technology and the durability and quality of the aftertreatment systems. We were able to collaborate with KTM to overcome the difficulty in achieving the OBD2 threshold limits, where they had aged the catalyst on the engine, but were not able to achieve the OBD threshold. Catagen were then able to step in and help age and degrade the catalyst further to ensure that the mill light would not turn on until the catalyst was significantly underperforming. So I want to give a bit of an overview of the methodology that we are able to apply to optimize the aging requirements to achieve OBD2 limits. We start with catalyst specification, including initial characterization of OSC, oxygen storage capacity, LIDOS, and a Lambda Sweep. And we also then are able to apply the WMTC, or the World Motorcycle Test Cycle data, which is fed into the Catagen Kinetic Model. We'll go into each of these in a little bit more detail soon. The model will then correlate the characterization results with the WMTC data to match the measured tailpipe emissions. And with a correlated model, we can now apply the OBD2 emissions limits to give target characterization results. We then were able to begin physical aging towards these characterization results using minimum checkpoints as we begin to understand the degradation rate. The iterations and checkpoints are required until we reach the target characterization, but this is to ensure that we do not overage or damage the catalyst. And then at the end of the process, a WMTC cycle was conducted to ensure that the emissions tests were still passed. So here we can see the results of applying this Catagen aging methodology to achieve the target tailpipe emissions. On the left-hand side, we can see the light-off curves as the catalyst is becoming more aged and how this correlates to tailpipe emissions on the right-hand side. So the target light-off temperature was determined through modeling and simulation of the WMTC drive cycle. And after only 3 iterations, we were able to achieve the OBD2 threshold limits. Now I want to go through a little bit more detail regarding accelerated aging of the aftertreatment systems. So in Catagen, we can offer a range of catalyst aging services from a standard bench cycle through to specific and unique aging cycles for R&D purposes. One example of this was as part of my PhD, I studied specifically the effects of oxygen. Therefore, being able to use the Catagen reactor, I could easily control the concentrations of oxygen in the system and the injection rates at which there was oxygen. You can see the 2 images on the right-hand side indicating the increased temperatures required to rapidly age a catalyst. An example of the benefits of accelerated aging, and if we apply the new legislations that are coming in, if you are aged a catalyst to 160,000 kilometers on a vehicle, it can take approximately 4,000 hours at an average speed of 40 kilometers per hour. But by aging the catalyst at hotter temperatures in the Catagen reactor, and depending on the catalyst temperature during a standard road cycle, the time can be reduced from anywhere between 150 to 400 hours total aging time. So some detail on the standard bench test or standard bench cycle as part of the legislation. As part of the Environmental Protection Agency, or the EPA, there are guidelines around accelerated aging procedures that can help to reduce the time required to have representative aged catalysts by increasing the aging temperature. The EPA define a specific legislative cycle which is used throughout industry around the world, the standard bench cycle. The SBC is a 60-second cycle with 40 seconds as stoichiometric, 5 seconds rich, where excess fuel is injected, representing an acceleration period. 10 seconds with secondary air, where air and fuel is injected together, which generates the exothermic spike in temperature. And finally, a secondary air injection, which would represent cruising or deceleration. During this, the EPA recommend that the catalyst bed temperatures are controlled to 800 degrees Celsius during the 40-second stoichiometric portion and a spike of 90 degrees Celsius during the exothermic reaction. The tolerance of this is plus or minus 10 degrees Celsius. However, here at Catagen, we have a much tighter tolerance. We can see these in the graphs at the bottom. So the left-hand graph shows the profile which the lambda and secondary air should follow. The middle graph highlights the lambda profile over the 60-second cycle and an 8-hour sample, showing excellent repeatability. And the right-hand graph is the bed temperature across an 8-hour sample, again showing a cycle well within tolerance for the 8 hours. An example of an alternative aging cycle is known as the fuel cut or lean spike, where the objective is to recreate a cruise or deceleration period of the vehicle where no fuel is injected and air only is flowing through the aftertreatment system. Again, the graphs along the bottom represent the lambda and temperature profiles. So if we move on to the aftertreatment characterization, it's very important to understand catalyst performance throughout its lifetime to ensure that tailpipe emissions will stay within the allowed tolerances and ensuring to reduce total air pollution. One of the most critical performance metrics of the catalyst and aftertreatment system is the oxygen storage capacity, or OSC. This is the only metric that is measured to determine catalyst performance while in use on the road. The OSC is also an important aspect to aid in reduction of tailpipe emissions. While the engine is running lean, the catalyst is able to store excess oxygen, and then when the engine is running rich, this stored oxygen becomes readily available to convert any hydrocarbons or carbon monoxide. At Catagen, we offer the industry-leading characterization, where we have a pure measurement of oxygen storage, critical for catalyst development and engine or powertrain calibration. During our OSC, we're injecting only nitrogen to maintain lambda 1. We then are able to inject air to measure how much oxygen is stored, and as can be seen on the graph, the difference between the inlet and the outlet lambda is the quantity of oxygen stored. We then have a reduction stage where CO is injected, and again, the difference between the inlet and outlet lambda is the amount of oxygen stored in the catalyst. For each OSC, we have 6 precision measurements for oxidation and reduction, and Catagen's typical operating conditions are 500 degrees Celsius at 12 grams per second. However, we can have a range of operating conditions, and we have previously investigated this to give us an OSC map, allowing full understanding of the OSC performance throughout the operating window of an engine. So catalyst degradation can also be tracked through the measurement of a light-off performance. The light-off temperature is the temperature at which 50% of the harmful gaseous emissions are converted to less harmful emissions. At Catagen, 2 separate light-off tests can be carried out, a fast and a slow composite light-off with gas of CO, HC, NOx, and then oxygen or air. The difference in light-offs is the inlet temperature ramp rate. A fast light-off ramp rate is approximately 10 degrees Celsius per second, and a slow light-off ramp rate is approximately 10 degrees Celsius per minute. The light-off tests are completed across the full aftertreatment system, and the emissions conversion are measured across the full system using industry standard analyzers with 50% conversion point of greatest interest. An example slow composite light-off is seen to the right, and the light-offs can be directly linked to tailpipe emissions, with the fast light-off representing cold start emissions and the slow light-off representing the catalyst performance during operation. It is important to understand both cold start and during standard operating conditions, as both can have significant impacts on the tailpipe emissions. Cold start is a current challenge, where the catalyst is required to get the operating conditions as quickly as possible to begin converting any emissions. The Lambda Sweep tests, or also known as air-fuel ratio tests, are used to assess PGM and wash coat degradation. And these tests are carried out in the Catagen Omega reactor, facilitating excellent control of gas composition. The test protocol here follows a cyclic oscillation of lambda with fixed HC and NO, and we vary CO and O2 to shift between rich and lean conditions. Fixed lambda rates were employed, facilitating an assessment of the impact of OSC on the emissions conversion. And as with the light-off test, the emissions conversion is measured across the catalyst brick using industry standard analyzers. The Lambda Sweep is an important catalyst performance metric because it allows us to understand the main operating window of the catalyst as the engine varies from Lambda 1. It can be seen in the graph that as the engine runs rich, the CO conversion drops off, but when the engine is lean, the NO conversion reduces. And the window of operation is another metric of showing OSC and how that helps convert emissions when the engine is to run rich or lean. So the main performance metric for the aftertreatment and total powertrain is the tailpipe emissions. And in order to measure the tailpipe emissions, it must be measured during the drive cycle. So most recent drive cycles are WLTC or WMTC, and then RDE drive cycles as well. So at Catagen, we have developed a new drive cycle procedure that allows us to replicate any drive cycle from the engine out emissions. And we can apply the AI and the software to match the catalyst inlet conditions for flow rates, temperatures, and gas concentrations. This allows for accurate, repeatable drive cycles, providing the best opportunity for optimum after-treatment development. We are then able to link the accelerated aging, characterization, and tailpipe emissions all together with the Catagen Kinetic Model. So the Kinetic Model has been developed to simulate catalyst light-off, drive cycle, and tailpipe emissions. The model uses the Langmuir-Hinchelwood approach for kinetics with the rate constant obtained from the Arrhenius equation and the innovations determined using the Foltz approach. The purpose of the model is to be used as a simulation tool to reduce the aging requirements and hence be used as a low-cost solution to obtain information regarding catalytic reactions and help to understand how various different designs, volumes, loadings, and applications will degrade in performance and over the lifetime of the catalyst. So based on catalyst specification and engine out or catalyst in conditions, the model can predict the conversion efficiencies and hence the tailpipe emissions. A common metric for tailpipe emissions is the cumulative emissions, and as can be seen in the charts, the simulated emissions correlate very closely to the measured tailpipe emissions. This close correlation in simulation allows for easy adjustable catalyst specifications to understand the impact on tailpipe emissions. An example of this would be to adjust the PGM loading and almost immediately see the impact on tailpipe emissions. So I'm now going to detail a current 4-year project which is ongoing and part funded by the UK government to aid Catagen in building the knowledge and understanding to significantly impact tailpipe emissions in the motorcycle industry. So Catagen and I have been awarded an FLF Award to become a future clean air leader of the motorcycle industry. We've been awarded a £1.2 million grant as part of a £1.8 million project, with the remaining contribution by Catagen to develop specific motorcycle test reactors and methods to aid the motorcycle developers to meet new emissions legislation in a cost-efficient manner. Catagen's ultimate goal is to continue to contribute to improved air quality on a worldwide basis and through the development of zero-impact vehicle emissions. In this specific project, we will be targeting the motorcycle industry. And the award will also develop me personally into a future clean air leader through a multitude of courses of leadership and collaboration courses at world-renowned industries or universities. As part of the government funding and award, I am building a consortium of motorcycle OEMs. The main purpose of this consortium is to further the development and understanding of the after-treatment and emissions control for the motorcycle industry. The consortium will be a 4-year program to investigate current and potential future concerns surrounding catalytic converter systems in motorcycles, including onboard diagnostics, OBD2, platinum group metals, PGM thrifting, oxygen storage capacity, OSC mapping, catalytic converter packaging, and a 5th work package, which will be agreed among the consortium members. Please, if anyone has any interest in joining the consortium, to further the development of motorcycle after-treatment system, reach out to me. And finally, thank you very much for taking the time to listen to my presentation today. Please feel free to reach out to our Indian partners at Gannett Solutions to arrange a call or testing services with ourselves, or you can reach directly to Dr. Andrew Woods or myself.